Okay, so do you have any questions before we start?
Bir şey soracaktım sadece. Bu ödevlerde mesela harmonik osilator dediği zaman ben mesela kuantum harmonik osilator mı alayım, klasik mi alayım, bir boyutlu mu alayım, üç boyutlu mu alayım gibi bazı soru işaretleri yaşıyorum ama.
Well, that's up to you. I mean, if we don't specify it, we can just choose whichever one you want. You can make assumptions. Well, we will start with one of the exam questions, in fact. We will look at a magnetic dipole. Well, you see, now our strategy is always same. Find the energy eigenvalues, label them somehow, and sum over them. Both in classical statistics and also in quantum mechanics, that is basically what we will be doing. So let's start with the energy. What is the Hamiltonian of a magnetic dipole? Well, if you remember your electromagnetics course, so this is the energy of the potential energy of a magnetic dipole in a magnetic field. Now, before going that, you see, if you have a magnetic dipole, typically it's the magnetic dipole of an atom or a molecule. It has the kinetic energy, it has all kinds of other energies. But one thing we had seen before was if you have n non-interacting particles, in that case, since the particles are not interacting, the partition function can be written in terms of the partition function of a single particle raised to the power n, and if they are indistinguishable, we also have an n factorial. Now, this is basically a separation between the degrees of freedom corresponding to different particles. But even if you have a single particle, well, it might have different degrees of freedom which can be separated. For example, you can have a Hamiltonian of a single particle, which will have a kinetic term, which depends only on momentum. And, well, it can have a, let's say, magnetic interaction. So if you look at the degrees of freedom or the microstates of this system, well, the microstates of this single particle will be specified by its momentum, its position, and the orientation of the dipole moment. So if when you are writing Q1, this will be sum over all microstates of h power minus beta h1, which is nothing but sum over the microstates, or the microstates are momentum, coordinate, and orientation of mu of h power minus beta p squared over 2m, h power beta mu dot b. But you see now, these summations over p and q and the summation over the orientation of the magnetic dipole moment, that's also, we can separate them. And so you have the single particle partition function will be separated, the single particle partition function corresponding to translational degrees of freedom, and the single particle partition function correspond to the magnetic dipole moment. So when we are looking for a magnetic dipole moment in a magnetic field, you can either say that, okay, this is a system where the dipoles, they are not free to move, but they can freely change their orientation. That is one way of looking at why we are studying this problem. Well, a dipole that is not allowed to move, how can you create that? Well, you can say that this is a solid, the atoms of the solid, they can vibrate around their equilibrium point, but since they are harmonic oscillators, they will be excited states will be higher oscillationary states will be excited only if kT is larger than or somewhat equal to h bar omega. So if the temperature is low enough so that kT is less than h bar omega, well, you won't be able to excite the vibrational degrees of freedom. So you can basically ignore them. So what remains is just the possible orientations of the magnetic dipole. So that is one way of looking at why we are looking at only the potential energy due to the magnetic field. Another way of looking at it is, okay, fine, it has all these translational degrees of freedom, but other degrees of freedom do not interact with this orientation of the magnetic field, in this model at least. So we are basically looking at what happens due to the orientation. So which can, well, we will look at this problem both classically and quantum mechanically. Classically speaking, H will be just minus mu times B times cosine of theta. Single particle partition function will be sum over e to power beta mu B cosine theta and sum over all orientations. Now the question is, what is the sum over orientations? How can we convert this to an integration?
Angles.
So you are saying that I can write this as d theta d phi.
From 0 to 2 pi.
Well, phi goes from 0 to 2 pi, theta goes from 0 to pi. Yes, this is not the correct summation over possible orientations. You see, you can just think of it as, well, if from d cubed mu, let's say that if the magnitude was also changing, then we would be integrating over all the components of mu, which we can also write as the integral over the magnitude times sine theta d theta d phi. So summation over orientations, in a sense, this is not equal to summation over d theta or d phi. This is a summation over d omega, the solid angle. So let's go back to our partition function. This is sum over the integral over the solid angle of e to power beta mu b cosine theta, or which is the integral over cosine theta from minus 1 to 1, the integral over phi from 0 to 2 pi of e to power beta mu b cosine theta. Well, nothing depends on phi, so that integral is just 2 pi. The integral over cosine theta will be e to power beta mu b cosine theta over beta mu b, when cosine theta changes from minus 1 to 1. So we have 2 pi over beta mu b e to power beta mu b cosine theta, mu b minus e to power minus beta mu b. Well, basically this is it. Well, let me look at the definition. So this is 4 pi over beta mu b sine hyperbolic beta mu b. This is Q1. Okay, one thing you should note that this is not a function of just the temperature, just the chemical potential, just the magnetic dipole moment, or just the magnetic field. It's a function of their combination. If you remember, when we looked at the harmonic oscillator, we had seen that the partition function, or the important thing in the harmonic oscillator case, it was beta h bar omega. In this case, it is beta mu b. Well, this is especially important because we will also look at the high temperature limit, low temperature limit. So the question is, what do you mean by high temperature and what do you mean by low temperature? The critical point is whether this quantity X is much larger than 1 or much smaller than 1. So that will be the definition of high temperature and low temperature. Because just saying that the temperature is high or low doesn't really make too much sense. For example, for U and B, 1000 degrees Kelvin is a very large temperature. But if you look at the neutron stars, 1000 degrees Kelvin will be, or several thousands of Kelvin will be a low temperature limit because of the characteristic energy scales there. So we have the n particle partition function, 4 pi times sine hyperbolic x over x raised to the power n. Well, these dipoles are localized, so we can distinguish them by their position. Just like the harmonic oscillator, you see, we said that the harmonic oscillators are distinguishable because they are oscillating at different points, around different points. So you can distinguish one oscillator from the other one by looking at around which point it oscillates. Similarly here, these magnetic dipoles are distinguishable because they are fixed. So once we have the partition function, practically we should be able to calculate everything. And one thing we would be interested in, for example, the magnetization. Total magnetic dipole moment. This is not the magnetization yet. Magnetization that you studied in electrodynamics is the magnetic dipole moment per volume. Well, let's look at mz, the z component of the magnetization, the component in the direction of the magnetic field. Well, the other components will be 0. So this will be just average of mu z times n. If we have n dipoles in total. So this will be n times average of mu cosine theta, which will be n times mu cosine theta, a to the power beta mu b cosine theta, divided by mu, well, without the mu, a to the power beta mu b cosine theta. Well, the denominator is already q1. Well, the numerator, we can write it as the derivative with respect to beta, or derivative with respect to b. But we need to also divide by beta of q1. You see, if you look at that exponent in the summation in the definition of q1, if you take the derivative with respect to b, that brings down a factor of beta mu cosine theta. I just want the mu cosine theta, so that's why I divide with respect to b. Or this we can write as n over beta, derivative with respect to b of the logarithm of q1, or n 1 over beta, derivative with respect to b of logarithm of q1 to the power n. Well, q1 to the power n is the n particle partition function. So this is 1 over beta, derivative with respect to b. Well, logarithm of the partition function just gave us the minus beta times the free energy. So the total magnetic dipole moment, the z component, will be just minus derivative of the free energy with respect to b. Well, this is also something we could have expected from the beginning. Remember, if you remember the first law of thermodynamics, this du is s dt minus p dv, or differential of the free energy. No, sorry, this is TdS. The differential of the free energy is minus s dt minus p dv. Well, there might be other influences that will change the internal energy of the system. For example, if the number of particles is changing, you can just add mu dn over here, also mu dn here. Well, if there is a magnetic field, the total magnetization, the magnetic dipole moment will also contribute to the energy. So this will be minus m dot dB. So m would be just minus derivative of free energy with respect to B, keeping all the rest constant. Well, I will use this notation of differentiation with respect to vectors. It's not a formally correct notation. You cannot differentiate with respect to vectors, but you can differentiate with respect to components of vectors. So whenever you see this notation, just interpret it as the components. So mz should be minus df by dbz, etc. And in fact, that is what we had also obtained from our treatment. Well, let's calculate this mz or mz0. Now this is the magnetization per unit volume. If I want to use the mz0 per unit volume, then it will be, let me take this one, but with the number density rather than the total number of dipoles. N0 is the number of dipoles per unit volume. Q1 we had already calculated. And this, let me just replace this with X. N0 over beta, derivative with respect to B of the logarithm of sine hyperbolic X minus logarithm of X. Well, I don't write the 4 plus the logarithm of 4 pi because that's just constant. When I take the derivative, it will be just 0. So this is N0 over beta. Derivative with respect to B is, first let me take the derivative with respect to X. The derivative of sine hyperbolic is cosine hyperbolic. Minus 1 over X. And then the derivative of X with respect to beta, B, where X, remember, is beta mu B. So this is equal to, if you take the derivative of X with respect to B, you get beta mu. So this is just, betas will cancel. And we are left with the magnetization as N0. This is the number density, mu times cotangent hyperbolic minus 1 over X. This is the magnetization of the system. Well, this function is given a special name. I said Liouville's function. I'm sure that I spelled it wrong. Just check the spelling.
Is it the Langevin function? Isn't this the Langevin function?
Yes. I said I spelled it wrong. Okay, Langevin's function. Now let's look at various limits. Let's start with the low temperature limit. So first, what does the low temperature limit mean? Well, T is small. Small in some sense, which means beta is large. And hence the low temperature limit is actually the limit where beta mu B is much, much larger than 1. This is what we mean by the low temperature limit. But you see, this low temperature limit, okay, on one hand, it's when the temperature is small, that condition can be satisfied. But that condition can also be satisfied when B is large. So basically, just like in fact in the case of the harmonic oscillator, you see on one hand you have the h bar omega, which is the characteristic energy of the oscillator. On the other hand, you have the temperature characteristic energy corresponding to the temperature. So low temperature will be when h bar omega is much, much larger than kT. Well, similarly here, if you have a magnetic dipole, mu b is the characteristic energy of this system. The energy of the dipole can be at most mu b, and the smallest minus mu b, so the characteristic energy will be mu b. So the low temperature limit is when kT is much, much less than mu b. Now, in this limit, what we would expect is, okay, there is the magnetic field which tries to align the magnetic dipoles in a given direction. On the other hand, there are the thermal fluctuations, which will just give energy to our magnetic dipoles, which means that it will try to randomly change the orientation of the magnetic dipoles. But if the temperature is low, these thermal fluctuations shouldn't have a large influence. So what dominates is the magnetic field itself. So the magnetic field will align the magnetic dipoles in its direction. So we would expect in this limit to have a large magnetization. So let's see what happens in this limit. You see, when x becomes very large, well, 1 over x is negligible. Well, cotangent hyperbolic 1 over x goes to 0. Cotangent hyperbolic x is e to power x plus, no, sorry, this is not cotangent hyperbolic, this is, no, okay, sorry. E to power x, e to power minus x divided by e to power x minus e to power minus x. When x is very large, e to the power minus x has become negligible compared to e to the power x, which becomes very large, so this is approximately 1. So magnetization in this limit is just n0 mu. So as you see, all the magnetic dipoles in the given volume is aligned with the magnetic field. Well, that's basically what we expected also at t equal to 0. There are no thermal fluctuations. Everything is aligned with the magnetic field. Of course, you can go ahead and try to estimate the first correction to this one. Then, okay, you have to calculate the first correction to 1. Okay, if you want, what it will be, I can write this as 1 plus e to power minus 2x divided by 1 minus e to power minus 2x. E to power minus 2x is a very small number, so you can expand it in terms of e to power minus 2x, which will be, I think, 1 plus twice e to power minus 2x. But again, this will be much, much smaller if x is large compared to this 1 over x. It's exponential. The contribution from the first term, from that cotangent hyperbolic, will be exponentially small for large x. But the contribution from 1 over x will be just polynomially small. So that will be the first correction. At small temperatures. So any questions up to here? Well, you see, there will be two things we will be interested in. One is what happens at various limits when the temperature goes to 0. So when temperature goes to 0, the magnetization is just given by n0 mu. All the dipoles are aligned with the magnetic field. Now that's kind of boring. So what we would like to do is, what about the first correction due to the thermal effects? And Well, to get the first correction, we basically need to expand in 1 over x. There is a cotangent, there is 1 over x over here, that's the correction. But then there might be also some corrections from the cotangent hyperbolic. But the correction to cotangent hyperbolic is exponentially small at low temperatures. So practically I can ignore it. The only correction is from my 1 over x. So that's what I wrote over here. Plus, of course, there are exponentially small corrections. Now let's look at the other limit, high temperature limit. Again, this time also the high temperature limit will correspond to, this is the thermal energy of the dipole. This should be much, much larger than the characteristic energy of the dipole. Or x is much, much less than 1. This is the limit we would like to look at, what happens in this limit. So what do you expect? Again, keep in mind that there are basically two competing effects we have here. On one hand, we have the magnetic field, which tries to align all the magnetic dipoles. On the other hand, we have the thermal effects, which kind of tries to randomly distribute all the dipoles. So what do you expect will happen at high temperatures? Yeah, thermal effects will start dominating, so the magnetic dipoles will be more or less randomly oriented. So we would expect the magnetization to go to 0. That is, in the strict limit, it will be 0. But then the question is, how does it go to 0? That's another question we will ask. Does it go exponentially to 0? Does it go polynomially to 0? So how does it go to 0? So what we should do is, here is our expression of the magnetization. We should expand this around x is equal to 0. So let's start with the, 1 over x is already expanded. There is nothing we can do about that. It diverges at x is equal to 0. So let's look at the cotangent hyperbolic x. How does it change as a function of x? This is e to power x plus e to power minus x divided by e to power x minus e to power minus x. Well, I can expand each one of those exponentials. I will keep terms up to x cubed. This will be 1 plus x squared over 2 plus x cubed over 3 plus 1 minus x plus x squared over 2 minus x cubed over 3 factorial. And the same thing in the numerator with the opposite side. Plus corrections of the order of x to the 4. I'm ignoring all the x to the 4 terms. Well, let's see. In the numerator, I have the odd terms, odd powers cancel. In the denominator, the even powers cancel. So we end up having 1 plus x squared over 2 divided by x, 1 plus x squared over 3, which will be 1 over x plus x over 2, I just divided by x, times 1 minus x squared over 3 plus corrections of the order x to the 4. Yeah, let me add that one. I'm expanding 1 over 1 plus x squared over 3 to the power minus 1. This is 1 minus x squared over 3 plus x to the 4 over 9 plus higher order terms. Well, I'm adding that term because of this 1 over x, because that x to the 4 term is a x cubed correction. So cotangent hyperbolic x is 1 minus x over 3 plus x cubed over 9. I'm ignoring now in the product all the terms of the order of x to the power 4 or more, plus x over 2 minus x cubed over 6 plus of the order of x to the 4 this is 1 over x. So 1 over x plus x over 6 minus x cubed over 18 plus of the order of x to the 4. This is cotangent hyperbolic of x. Okay, what do I need? I have this expansion. So this is x close to 0. This will be n0 mu. Well, you see 1 over x's will cancel. You see at x is equal to 0, although 1 over x seems to diverge, cotangent hyperbolic also diverges. So the result is still finite. We don't have a divergent magnetization. We expect the magnetization to be 0. And what is left is x over 6 minus x cubed over 18. So this is so you see, as we expected, as temperature increases, that is as x goes to 0, the magnetization also just goes to 0. And in fact, this is, I can just ignore the x cubed term also at very small temperatures. This is n0 mu. X was, now let me keep it as x, mu 0 b x over 6. Well, there is another quantity about magnetization. Yes, if you remember your electrodynamics courses, okay, if you put a medium in a magnetic field, it will be magnetized. And the magnetization is determined by the so-called magnetic susceptibility. And if you remember, magnetization was defined as chi times B. Now, this is, of course, at the linear, so-called the linear approximation. Real materials have other corrections, B squared, B cubed term corrections, but at least for, if you don't have a ferromagnet, this will be the relation between magnetization and the magnetic field at linear order, at leading term. We can write this as magnetization is defined as derivative, the magnetic susceptibility is the derivative of magnetization with respect to B evaluated when the magnetic field goes to 0. So in our case, chi will be derivative with respect to B of n0 mu. Well, x is beta mu B. Well, this is equal to n0 mu squared divided by 6 kT. This is the magnetization at high temperatures. As you see, as C goes to 0, the magnetic susceptibility also goes to 0. Well, this is so-called the Curie law. And C is the Curie constant. Well, there's a factor 2 I'm missing somewhere.
Curie law calls for high temperature test.
Well, Curie law describes how the magnetization disappears when you increase the temperature of a magnet. You take any magnet. Well, here this is not a ferromagnet. This is not a take any magnet. This derivation is not applicable to a ferromagnet, but take any object. If you heat it to large enough temperatures, the magnetization will just disappear. Now, this was, of course, if you note, this was the classical treatment. So we have a magnetic dipole, which can have any orientation that you like. We just summed over all possible orientations and obtained a classical result. Now, let's also look at the same problem from a quantum mechanical perspective. Let's just imagine electrons in a magnetic field. It's enough for us to calculate a single particle partition function, which will be sum over all states of e to power minus beta e, whatever the energy eigenvalues are. The Hamiltonian of the system is given by e over 2m, let me write it in this form first, j dot b. Magnetization, magnetic dipole moment is given by g e over 2mj. Okay, this is what your book says, but that is not correct. Well, I will stick with the g is, well, let me, 3 over 2 plus s plus 1 minus l plus 1 over 2j, j plus 1. Well, the final result in the book is still correct, but this is not the interaction how an electron interacts with a magnetic field. Well, the Hamiltonian will be, well, there is the e over 2m factor. If the electron has a spin s, well, due to its spin, it has a magnetic moment, and hence it interacts with the magnetic field. If it has angular momentum, it also has, it's moving. A moving charge interacts with a magnetic field. So the correct expression will be L plus 2s dot b. This is the interaction of an electron with an external magnetic field. You see, J is L plus s, but there we don't have L plus s, we have L plus 2s. Or if you choose the magnetic field to be in the z direction, this is E over 2mbz, Lz plus 2sz. Or let me say just B. Well, the energy eigenvalues is still, you can say that the energy eigenvalues are still determined by this term over here. No, not that term. Yeah. Well, let's see the energy eigenvalues. Rather than, well, there's a minus sign. Yeah. This minus sign is since the electron has a minus charge, so that is why in the Hamiltonian I don't get a minus sign. There's a minus sign plus there's the negative charge of the electron, so that's plus. So to calculate the energy eigenvalues, rather than looking at the h directly, let's look at h squared. Well, h squared is e over 2m b squared. This is mu b. This is called the Bohr magneton. Lz plus 2sz Now, what is the direction of z? Well, I don't know the direction of z. It's an arbitrary direction. So let me choose the direction of j as my z direction. So these are all I'm just taking the scalar product with the vector j and dividing by the magnitude of that vector j, so that if j is the direction, if z is the direction of j, this will be fine. You see, I have already defined the direction of b as my z direction. But then I'm looking at, okay, Lz plus 2sz, I'm looking at that separately. Well, the direction of z is arbitrary for that factor only. So I'm choosing that z direction to be the direction of j. But then L plus 2s dot j is L plus j, L dot j plus 2s dot j, which I can write as minus 1 over 2 j minus L squared minus j squared minus L squared minus j minus s squared minus j squared minus s squared. Well, you see, j is L plus s. So this is L squared, this is s squared. So this is equal to minus 1 over 2 ss plus 1 minus j plus 1 minus L plus 1. And the second term is minus L plus 1 minus j plus 1 minus s plus 1. And let's simplify it a bit. I have 3 over 2 j plus 1, and then plus 1 over 2 L plus 1 minus 1 over 2, no, this is plus, by the way, sorry. Now j factor is plus 3 over 2, L factor is, yes, minus plus 1 over 2 s plus 1. So let me take out the j plus 1 out. This is 3 over 2 plus s plus 1 minus L plus 1 over twice j plus 1. And this is actually the g factor that's quoted in the book. I don't like this derivation that much because j is an operator. So at some point I set the z to be the b to be in the z direction. At the other point I choose it to be the direction of j. But the answer is correct. So if you look at the energy eigenvalues of the system, the energy eigenvalues are given by G mu B. G is this so-called Lande. This is the Lande factor. G mu B Jz. This is the energy eigenvalues, and practically this is all I need. And the eigenstates will be eigenstates of J and Jz. So the single particle partition function will be e to power minus G mu B times, let me call that M, sum over M from minus J to J. There's also B. So what is that sum? So how do you calculate this sum? Well, this is basically M from minus J to J e to power minus G mu B times B raised to the power M. Some constant raised to the power M, and you are summing over all M. So how do you calculate such sums? Guys, it's easy to forget if you memorize the formula. But it's easy to remember how to derive such formulas. So let's see. Let's suppose that we are trying to sum from M is equal to A to B of x to the power M, which will be x to the power A plus x to the power A plus 1 plus x to the power B minus 1 plus x to the power B. Let me multiply the same thing by x. Well, this will be x to the power A plus 1, x to the power B minus 1, x to the power B plus x to the power B plus 1. Just subtract side by side. You get 1 minus x to the power M will be x to the power A minus x to the power B plus 1. So this sum is x to the power A minus x to the power B plus 1 divided by 1 minus x. Now, if you don't remember, just learn how to derive. You see, the derivation is just a couple of lines. Well, so back to our partition function, Q1. X to the power A is just the first term. So it's e to the power J, G mu B times B times J. Minus x to the power, well, B is just J minus G mu B times B times J plus 1. Now this is E. Divided by 1 minus e to the power minus G mu B times B. Again, if I didn't do a mistake, this is the partition function in the quantum mechanical description. And by the way, I forgot to put the beta factor. Okay, let's use this definition. X will be beta G mu B times J times H B. To simplify it a bit. So Q1 will be 8 power X plus 8 power minus X times 1 plus 1 over J divided by 1 minus 8 power minus beta J. Beta over J. X over J. Well, let me multiply both sides by X over 2J. So that this becomes 8 power X 1 plus 1 over 2J. So this is minus 8 power minus X 1 plus 1 over 2J divided by 8 power X over 2J minus 8 power minus X over 2J. So this is sine hyperbolic 1 plus 1 over 2J times X divided by sine hyperbolic X over 2J. Okay, that's our Q1. Now the next thing we need to do is, okay, so now what we are interested in, magnetization. Okay, so the above derivation of magnetization this is still correct. This is still correct because that derivation didn't really make any assumption about how we summed over the microstates. So whether we summed over the microstates, taking the microstate as quantum mechanical state or classical state, I don't really care in this expression. But let's give our 10-minute break now, and then we will look at what does the quantum mechanical system tell us.
Bu N0'yu neden, yani zero'yu neden eklemiştik?
You see, N is the number of dipoles. N0 is the number of dipoles per volume. Or basically N over V. Because magnetization of a system is defined as the magnetic moment per volume. This is what we call the magnetization. Magnetic moment density, if you like. Magnetization is defined as the magnetic moment density. So I don't use the number of particles, number of dipoles, but the dipole density in defining the magnetization. Other questions? Yes, the derivations will be more or less straightforward. Again, we will basically do the same thing. We will take the derivatives to calculate the magnetization, magnetic susceptibility. We will look at the low temperature and the high temperature limit. Well, the limits will be slightly different because you see here, this is what we call X. Before, what we had was beta mu b. Well, if you compare the two terms, you see mu is somewhat similar to g mu b and j. Mu in the classical limit becomes g mu b j in the quantum mechanical case. And x very small, well, x very large, for example, can mean very different things. High temperature, that is when x is very large. No, x is very sorry. X is very large is low temperature when beta is large. X is very large would mean very large magnetic field. Or you can go ahead and say maybe mu is very large. J can be large. Now we will also look at the case when J goes to infinity. You see, we are looking at a quantum mechanical system. But somehow we need to recover the classical limits in certain limit. And that limit will correspond to large quantum numbers. That is when J will be large, huge. So that the direction, orientation of the magnetic field is almost arbitrary. But we don't want the mu to be able to compare with the classical limit. We don't want mu to become very large. So the limit we will take will be J becomes infinitely large, but G becomes infinitely small, so that the product will still have its fixed value. And so that will be the limits that we will study. Okay, now let's give our 10-minute break and we will continue.